All right, your tests are graded. I don't want to hand them back yet because there's still some people who need to take the test. If that's you, either in person here or watching online, please do so quickly so we can get that done. This next unit, it covers a lot. I don't know how else to say it. Just warning you up front. This week is mostly conceptual. Like FTC is fundamental theorem of calculus, and then second FTC would be the second fundamental theorem of calculus. Those are very conceptual topics. The next week is integration by substitution mostly. That's more process oriented. How do I actually do that? So this has a lot of both. A lot of new concepts and a lot of new, like integration is, going backwards. Antiderivatives. So you did that on the last test, but those were all the straightforward ones. I hope you didn't think that was the hard set, because that was the intro set. Okay? And most of you did them well, which is good, but that's just that's the tip of the iceberg for where we're headed on integration or going backwards, antiderivatives. So there's a lot on this next test coming up. It's also 2.5 weeks worth of stuff. So don't get behind. Don't mail it in. Don't think, I'll catch up later, because it will snow you under in a hurry on this one. I'm also going to have to pick up homework somewhere before the end of somewhere early next week probably. Maybe that Tuesday. Take up everything up till whatever. So I haven't figured that out yet, but I'll take up homework way before we get to test day. All right, let's start with what should be, knock on wood, relatively easy warm-ups. The first one is, you tell me, what's the difference between those two things? One has limits and one doesn't. So how are you going to do these two separate problems? Or what makes, they look a lot alike, but you're going to work them very differently. One of them's area, one of them's antiderivative. Which one's which? Yeah, the first one's an antiderivative with algebra first, right? Some of you didn't do that on the test. You can't antiderivative the top and the bottom separately. You've got to do algebra first.
Oh my God, this was the best question.
It was something really close to that. They're really close to that. Not exactly that, but close. So the first one's an antiderivative with some algebra up front. The second one's an area question, even though they look really, really similar. So do both of those. We'll go over them, and then we'll talk about why they look so similar. Oops, you need a hint for this first one. We've seen this before, but hint, the natural log of, that's the answer. The antiderivative of 1 over x is the natural log of x. So on the test that didn't happen, it was x to the negative 2. So you could use the power rule. But when it's x to the negative 1, the power rule won't work. All right, let's go over these. So if I underivative x, where did that come from? Who was his antiderivative? X squared over 2. And who has a derivative of 3? 3x. And then that was my mistake for that to show up. But the antiderivative of x to the negative 1 is natural log of x. And then don't forget the plus c. So sometimes that integral symbol means take an antiderivative. Sometimes it means find the area under the curve. An equal sign feels a little bit weird, but this is really what we mean. So 2x, so that would be up 2 over 1 from 0 to 3. So 3 in that spot, or that length would be 6. Area of a triangle is 1/2 base times height. 18 divided by 2 is 9. So that equals, that is not quite right? The answer is not the picture, the answer is 9. Okay, today, this is the big connection. This is the fundamental theorem of calculus. It's like, why in the world did we keep using this same symbol for two seemingly very different things? Like antiderivative is, like, that's calculus, like hard calculus. Like, how do I go backwards? That's weird stuff. And then area, I'm like, well, that's not bad. As long as I know as long as I can graph that, then I can do the area under a curve. That's not that big a deal. That's like geometry. Here's the connection. I'm gonna work a problem like this, and then I'll get to the technical stuff. So let's don't even put any limits on there. Let's just do the integral from nothing to nothing, just the integral of 2x. So that would be x squared. Plus c. Plus c. Now, again, this is just going to be voodoo mystery magic stuff going on here at first. Well, let's say there was a 0 and a 3 there. What this means, or how we can use this, is those are our limits of integration. I call them that there. We call them that here. We're going to plug in the top one, and then we're going to subtract. We're going to plug in the bottom one and subtract. So the top one plugged in minus the bottom one plugged in. So 3 squared plus c, we still don't know what c is, minus 0 squared plus c. Well, 9 plus c minus 0 minus c equals 9. Not a coincidence. So here, this is the fundamental theorem of calculus, is that if you do the antiderivative, it equals the area under the curve. If you do the antiderivative with limits, I guess I should say, because without limits we just had x squared plus c, that didn't really help us. But the antiderivative with limits is also equal to the area under the curve. So today we join the two things. It's not these two separate ideas. It's like, that's why this symbol is used for both. You can do it either way. You can find the area with geometry sometimes, but you can also do an antiderivative, plug in the limits, and that tells you the area. Antiderivative with limits equals area under the curve. That's the really unprofessional, slangy way to say that's the fundamental theorem of calculus. That's the connection that we've been writing right up against. We didn't do it on the last test because it's hard enough to do antiderivatives. It's hard enough to do area under the curves. So the last test there was a bright line in between those two things. We did a bunch of these questions, we did a bunch of those questions, and we just kind of pretended they weren't related to each other other than that symbol. And now we understand that they go together. All right, that's a long intro into, here's the official stuff on the fundamental theorem of calculus. Fundamental theorem of calculus, right? If a function f is continuous on A to B. Again, that continuity thing is important again, because if it's not continuous, then there's maybe a jump or a gap or an asymptote, and that messes up the area stuff. So as long as the function is continuous. And then here's some new symbols, or using symbols in a little bit different way. Capital F is an antiderivative of lowercase f. Right? We need a way to talk backwards. Like moving forward, the derivative of f is f prime, and the derivative of f prime is f double prime. We just keep adding primes. But if we want to back up one from there, how do we say who was the antiderivative of f? We use a capital F. Then the integral from a to b of f of x dx that's usually what we think of as the area under the curve from A to B, is equal to capital F of B minus capital F of A. And capital F is the antiderivative. Antiderivative evaluated at B, so minus the antiderivative evaluated at A. Anti-evaluated at A. So that's what we saw on the little triangle that we did at the end of the warm-up there. The area under the curve, we can find the area under the curve by doing an antiderivative. So this will help us when we get shapes that we don't know what they look like. If we want the area under the curve, we can use antiderivatives to get there. Let's do some examples. Today is going to be pretty straightforward examples of just making the connection between the two things. So the integral from 2 to 3 of 4 over x squared plus 1 dx. So the area under the curve from 2 to 3 of that thing. Obviously this is not a candidate for geometry because I don't know what that looks like. So instead we're going to use the antiderivative. Although I think first I'd do some algebra, because I don't really want to do an antiderivative of 1 over x squared. I'd rather make it x to the negative 2. Alright, so the 2 and the 3, we'll worry about those at the end. Our first job is to find the antiderivative of this thing. So x to the negative 2, that one was on the test. So if I increase the power by 1, if I start at negative 2 and I increase that by 1, what do I get? Negative 1. And then I'll divide by that new power. And obviously I can clean that up a little bit, but that's my first pass at it, is increase the power by 1 and divide by the new power. What function had a derivative of 1? Just x. Now normally we would have to put the plus c on there, but because of the subtraction thing that we're about to do, like every time, we don't have to write plus c when we know that it's going to be plus c minus c once we plug in 3 and 2. Right? So if you want to, you can. What the heck, I'll do it one more time. This is the last time I'm going to do this because this is unnecessary. I don't really know what c is, but I don't have to know because it's subtracted and goes away. clean this up. That would be negative 4 over x plus c from 2 to 3. So we want to evaluate it at 3 minus evaluate it at 2. Evaluate our antiderivative at 3 minus evaluate it at 2. So negative 4 over 3 plus c minus, distributing the minus sign becomes a huge deal on almost all of these problems because it's minus all of the stuff, so make sure the minus sign goes to everybody. Negative 4 over 2 plus c. And you know what? That'd be a safe stop. Most people wouldn't stop there, but that would be a safe stop. I think even with the c's in there, because they go away, c minus c is 0. Now, we're looking that up in the book. It's not going to leave it there. It's going to do the math here. So negative 4/3 plus 3. I can see already the c's are going to go away. Plus 2 minus 2. Distributing the negative sign. In fact, anywhere in here I could pull the plug on this and be like safe stop. I don't want to mess with fractions. I'm good, thank you. Even the 2 minus 2, but whatever, I'm fine. Leave it alone. Again, multiple choice of the book is going to go ahead and negative 4/3 plus 9/3 would be 5/3. So if you're checking Calc Chat, then you're going to get 5/3. But you could safe stop it well before then. Safe stops you do have to plug in. You wouldn't be able to you certainly couldn't leave it here because that's still calculus left to do. And that's not calculator ready. I guess that's, even with the c's in there, that'd be calculator ready because whatever your calculator thinks c is, they would cancel out. I don't know, I'm hesitant with the c's. You could definitely stop here though. That one would definitely be okay. So antiderivative, plug in limits. That's all we're doing today, and trying to get in our heads this connection between the antiderivative is the area under the curve. Or I can find the area under the curve by finding the antiderivative. Integral from 1 to 9 of x minus 2 over square root of x. Well, another one, this is not a good candidate for geometry because I have no idea what that looks like. So let's do some algebra first. Let's see, square root of x would be x to the 1/2. And then if I divide them both by x to the 1/2, right, that's x to the first over x to the 1/2 would be x to the 1/2 minus 2 x to the negative 1/2. Increase the power by 1, divide by the new power. So if I increase 1/2 by 1, be 3/2, and I don't really want to divide by 3/2. I'd rather multiply by 2/3. And again, you can check that. 3/2 times 2/3 would go away, and then 3/2 minus 1 would get you to 1/2. All right, the second piece is going to leave the minus 2, and maybe it gets altered here in a minute. If I add 1 to negative 1/2, I get a positive 1/2. And I need to divide by the new power. But I don't want to divide by 1/2. I'd rather multiply by 2. So and another 2 shows up there. And then the symbol is, I've already taken an antiderivative, So it's like now on the back side of that, I'll put the 1 and the 9. I want to evaluate that at 9 and evaluate that at 1. So 2/3, 9 to the 3/2, minus 4 times 9 to the 1/2, minus, oh, this time I dropped the c because I've only done 2 of them, but every single time it's plus c minus c, so why bother with it? Minus, now I'm going to evaluate at 1, 2/3, 1 to the 3/2, minus 4, 1 to the 1/2. And as ugly as that is a safe stop, because you could pipe that into the calculator and get some answer. Now, there's some exponents in there, and some of us may be a little weak on exponents. I'm going to keep working this because that's probably a multiple choice type question, and we won't stop at a safe stop on multiple choice. So I'm going to keep going just to review our exponent rules here. See, the top number is the power and the bottom number is the root. Remember this from whoever taught you. Flower power grows on top and the root grows underneath. So the square root of 9 is 3, and then 3 cubed. 2/3 of 27 would be 18. Half power is square root, so 4 times 3 is 12. The others are all 1, so that's kind of nice. Minus 2/3 minus 4. Running out of room, but that would be 6 minus 2/3 plus 4. So that would be 10 minus 2/3. Obviously, anywhere in here is a safe stop. You stop anywhere you want. Although, if you recognize the safe stop was possible, you probably should safe stop right there rather than risk messing this up. 10 minus 2/3 would be 9 and 1/3. Or, on the multiple choice test, it's probably going to say 28/3. So again, if it's your choice, safe stop it. Don't mess anything up. Multiple choice test is probably going to test that you can take care of all those exponents. But big picture, apart from the details of the exponents, antiderivative, evaluate at the top, minus evaluate at the bottom. Let's do one more. Because we don't want to let a day go by where we don't do some trig. The integral from 0 to pi over 4 of x minus secant squared x dx. Again, that means the area under the curve from 0 to pi over 4 of that graph, but I have no idea what that graph looks like, so I'm not even thinking like geometry, graph it. I can't do that. I'm going to do the antiderivative. So the underderivative of x, we did that one already, x squared over 2. And then what function has a derivative of secant squared? Tangent. Look at you guys, experts. And then now we've taken the antiderivative, so I don't want to use the antiderivative symbol. Like I already applied the antiderivative symbol, so that's gone. Now I'll evaluate from 0 to pi over 4. So again, the first one, the top one minus the bottom one. If you want to use the capital letters, you can. To kind of tie it to our original definition. The antiderivative at pi over 4 minus the antiderivative at 0. So pi over 4 squared over 2 minus tangent of pi over 4 minus 0 squared over 2 minus tangent of 0. Here's good news for those of you that are not big fans of trig. That is calculator ready. Like, you can type that in the calculator and get an answer. So that is a safe stop. On a free response question, I would stop there. Like, even if you know what tangent of pi over 4 is, like, why risk it? Like, maybe your brain jumbled something up and you forgot it that day. Like, leave it alone. Leave it as is. Again, multiple choice is probably going to... So 4 squared is 16. 2 is also in the bottom, so that'd be pi squared over 32. Tangent of pi over 4. Well, you're at the right spot, right?
It's the diagonal.
It's the one that's in the middle. Both the sides are root 2 over 2, but that means the tangent of it is 1. 0 squared over 2 is 0. Tangent of 0 is 0. That's a lot of zeros there, but... So, again, back of the book is going to say pi squared over 32 minus 1. You're probably going to say, why am I messing with that? That's calculator ready. If you want to know the tangent of pi over 4, you figure out the tangent of pi over 4. Right? That's not calculus. That's not my problem. All right, the assignment, page 288, 5 through 37, every other odd. All right, 5, 9, 13, and so on. And I'll take a picture of that and post it in Schoology, because apparently the online textbook somebody said was having issues. But I'll post a picture.